want to do some examples to that we were going to cover in class, but we just didn't have enough time. And just to clarify some things about functions. So let's look at the oral exercises. It's on 144, but it's the oral number 15. Some people got to this, some people didn't. And they give you a graph, and it's a straight line, and that point is 3, minus 1. And then it goes up to 3, 4. And it's a straight line. That's not super crucial, but it is crucial that it's something like a straight line. And that's the graph of a function. Let's call it f if we need a name for it. And we're asked questions about f. And what we're asked here is these two words, the domain and the range. And the book has the definitions of this, but let's just go over it real quick. Domain is all the possible inputs to the function. If you think of a function as a machine or a process, then that's all the things that are legal to put into the function. In this case, you're asked to assume that this is the entire graph of f. It's very tempting to extend that straight line off to infinity and say, oh, I think you could put any number into that. But they're saying, no, this is minus 3. Yeah, you probably noticed that. That's minus 3, minus 1. I'm just clueless here. Okay. This function is you're only allowed to put in the inputs from minus 3 to 3. For example, maybe this is the input. If you look at the meaning of the input, maybe this is some, what goes from minus 3 to 3? Maybe it's like the temperature in some reactor, and it's just not physically possible for that temperature to be anything between minus 3 and 3. Okay, so the domain is all the possible inputs. When you graph a function, that's always graphed on the horizontal axis. So the inputs here are basically the possible x values, and so that's going to be a set in a number line. Well, let's just graph that. We know how to graph that. So graphing understanding domains and ranges amounts to graphing on a number line. Now, what's the algebraic correspondent to that? It's inequalities. The algebraic way to describe that is that's all the x's that are between minus 3 and 3. The really fancy way to say that is set builder notation. It's the set of all the x's that satisfy a certain condition, and that's that they're between minus 3 and 3. So that's a very good official way to do that. Now the range is what are all the y's that result? What are all the outputs of the function that result? And when we graph a function, the output is put in the y variable. So this is going to be a set of y values. In this case, it happens to be pretty simple. It's everything between minus 1 and 4. Now, if this function had gone up to some weird, hard-to-figure-out maximum and then come down, this would be a much harder question. We kind of have to eyeball that and say, well, how high did that get? Or if it wiggled all over the place, maybe it went down here. Oh, how low did it get? That would be harder. In this case, it's pretty clear that it's exactly between minus 1 and 4. Okay, so the domain is the set of x values. The range is a set of y values. When x is the horizontal and y is the vertical. Sometimes the letters are going to get switched around because there's some reason why we want x and y to switch. That can get confusing. But if we're using our standard letters, it's horizontal x, domain, vertical y, range. Now, there's another notion of domain which is just subtly different, which if you look at, for example, problem 32. So now let's go to the written. This is one that people were struggling with. Much harder question, I think. Here, capital F of x, believe it or not, sometimes it can matter whether it's a capital X or capital F or little f. They're just trying to get used to the fact that there's lots of different letters that typically get used. Here, they just give you a formula for f. A formula only. And then they ask its domain. And you might say, well, you didn't tell me its domain. You tell me what the legal inputs are. Okay? In this case, where it's only given by a formula, unless told otherwise, we're supposed to assume that the domain is absolutely all possible x values which produce an output, or which make sense. Okay. So if you can put an x in and it produces some actual real number for an output, then that's going to be in the domain. And we're not going to artificially restrict it unless somebody tells us to. So you've already seen that. If you look at the homework, I'm going to compare this to problems 29, 30, and 31. That's a place where this notion comes in. So this would be actually a really good time to stop the video and go do 29, 30, and 31, because those are sort of simpler versions of this idea. Just think about all the possible x's that don't work, really. Actually, that's the easy way to think about this is, are there any x's that don't work? If not, the answer is all real numbers. But sometimes there are formulas that just don't make any sense with certain x's. So let's just do a little bit of trial and error here. Would x equals 2 work? Yeah, square root of 4 minus 1 equals square root of 3. That's fine. Would x equals 0 work? Square root of 0 minus 1. Oh, that's not good. Okay. You can make sense of that using complex numbers, but that's not what we're doing here, that's for sure. Not a real number. We're going to exclude that. X equals minus 1? Even worse. No. Okay. So somewhere between x equals 2 and x equals 0, it stopped being true. Let's go back. Let's say x equals 5. Oh, that's fine. That's the square root of 10 minus 1. Oh, that's actually a perfectly nice number. Okay. So somewhere between, it looks like for big numbers it works, because we get positive things inside the square root. For small numbers it doesn't work. Well, what does that look like? It looks like if we had to guess what the region of x is where it's legal, in other words, the domain, looked like, we notice that let me put 0 here and x here. This doesn't work. This minus 1 didn't work. Probably all these don't work. And then 2, that did work. 5 did work. So probably everything over here does work. And somewhere in here it's going to stop working. Well, that looks like, again, probably the solution set for an inequality. And this is where it can get tricky, but there's a systematic method here. You look at this formula once again, and you identify the part that actually goes wrong. If I put an x in it, does it go wrong to double it? No. Does it go wrong to subtract 1? No, we can always do that. What goes wrong is the square root part. And so what we're really interested in, and we know where the square root of blah doesn't exist, it's exactly when blah is less than 0. Let's make it a little more positive. It does exist when that thing is greater than or equal to 0, when it's a non-negative number. So what that says is it's going to work exactly when whatever is inside the square root is greater than or equal to 0. A lot of people get confused and jump to the conclusion, no, I think it's when x is greater than 0, or greater than or equal to 0. But that's not what the square root function sees here. It's seeing the quantity 2x minus 1. There's a lot of subtlety to this problem, and I think it's fun to jump into it, but if this is confusing, that is you share that with every student in AB Calculus, for example. So if we solve that inequality, it turns out, yes, the set of legal x's is exactly one of these sets. That's the solution to a simple inequality. It's everything where x is 1/2 or greater. That's the magic number. If we put in 1/2, you get 2 times 1/2 is 1 minus 1 is 0. Square root of 0 is 0, that's legal. But if it's anything less than 1/2, it's bad. If it's anything greater than 1/2, it's okay. Okay, I'll stop there. I think you can do the rest of the homework. with that.